So, I'm going to teach you how to find eigenvalues in vectors, because I need to be able to find eigenvalues in vectors in order to solve differential equations of the form y prime is a matrix times y. Like the thing I just developed said, if I could find y that was x e to the lambda t, I'd be done with this, but x and lambda have to be an eigenpair, and so that means I need to learn how to go hunt for eigenpairs. So, first things first, you need to find a matrix, or sorry, you need to find a vector and a value so that multiplying by this matrix is the same thing as multiplying by a scalar, right? So you could write that equation down and like go hunt for it, or we can use this shortcut. Anybody who's had linear algebra know the shortcut?
To find the determinant thing?
Yeah, the determinant thing. So you take your matrix A, subtract lambdas from the diagonal.
Normally it'd be like 7 steps to get there, I think, right?
What, to demonstrate that this is the
If you really
appropriate thing?
Yeah.
Yeah.
Then take the determinant of that and set it equal to 0.
Don't you have to swap the,
No,
What's that?
because there's actually 2 ways to do it.
Yeah, so which side I subtracted what from at the beginning, turns out it doesn't matter at all.
that's annoying, I'm sending that.
Right, so you could do either A minus lambda I or lambda I minus A.
Yep.
Doesn't matter which, don't
Set it
care,
to 0.
pick one. Right? So now how do you calculate a determinant of a 2 by 2 matrix?
Multiply and
AD
subtract.
minus BC.
So this will be familiar from Calc 3. It's that one minus this one. So the product down the diagonal minus the product across the anti.
We did that in Calc 3.
We did. A bunch of times. Like when you're making cross products,
Oh, yes.
right? Remember you cover up a row and a column and then what's left you do this minus that? Same thing. And for the same reason actually. Because linear algebra.
Primitive matrices we were kind of working with?
Yeah.
Okay.
So I have minus 1 minus lambda times minus 1 minus lambda.
Looks like minus 1.
So that'd be minus 1 times minus 4 would be plus 4, and then I'm subtracting it, so I have minus 4 is 0. Foilings.
1 plus 2 lambda, or minus 2 lambda. No, it's plus lambda squared.
Okay. Foiling. Then by my terms, lambda squared plus 2 lambda minus 3 is 0.
So you get 3 and negative 1.
Factor. Plus 3 and lambda minus 1. Other way.
No, it's right.
No.
Yeah, that's right, yeah.
Nice try. Almost had me. Factor, then what?
So, for each one.
Then you have your eigen.
Yeah, so zero product rule this thing. That's going to give you your 2 eigenvalues. So your eigenvalues are lambdas minus 3 or lambdas 1. Okay? Then what?
Solve
Take
their
a lambda, plug it
solve
back
for the
into.
basis of their eigenspaces.
Not that hard.
Okay.
Say that, but easier.
Plug it in.
Plug it in. Plug it into what?
Your determinant, or not determinant, the matrix before the determinant.
Yeah, so remember I had this equation at the end of the last thing. I had a minus lambda I times x is the 0 vector, right?
Yeah.
So what I just figured out is the lambdas. I now know lambda is either 1 or minus 3. So now I'm going to take that and go solve for x. This is really easy when these are different. Like if this is a whole list and they're all different, life is really chill. You just take each one.
Say we get a square right there, right, with the lambdas?
Yeah, we're not going to talk about that.
Okay, I just wanted to know if it was,
No, we're
if
not
it was
going to
just
talk.
one
No,
value
we're
or
not
if
talking
it's
about
repeated
it.
values.
We're not talking about it.
Okay, cool. Won't stress then.
Oh, dang it, I erased that thing. So, for lambda is, I'm going to pick the easy one first, minus 3. So for lambda's minus 3, I'm plugging in there, right? So I have my a, that's this thing, minus lambda's down the diagonal. So that's minus 1, minus 3.
Yeah.
I mean minus 3, plus 3, like I said. And then minus 4 and minus 1 and minus 1 minus 3 again. So this is my a minus lambda I. So this is a plus 3i, right? And I need to multiply that by some vector x and get the 0 vector out of this. You guys see that? Okay, so a little simplification. Minus 1 plus 3 is 2 in both spots there. So I have a matrix that looks like 2, negative 4, and negative 1, 2.
And this will always be a dependent set, huh?
Yeah, and this will always be a dependent set because you made it a dependent set. Like you forced that. Yeah, because you set the determinant equal to 0 and then solved it and then plugged that back in. Like you broke this on purpose. Like you did that. That was the thing you wanted.
So since it's always dependent, we don't even need to ref, we can just look at the first row and...
Yeah, and you don't need the second row. If it's a 3 by 3, then you got a little work ahead of you, right? But if, in the 2 by 2 case, the only way that picking this up and dropping it onto here is going to give you 0 in both rows is if it's perpendicular to both those vectors. And there's only one way to be perpendicular to one of these vectors, right? So pick the one with the easiest coefficients in it. So this would tell you that your bottom thing is minus x1 plus 2x2 has to be 0, which tells you x1 is 2x2. You guys see that? So your eigenvector for lambda's 3 looks like
2, 1, maybe?
1,
2, 1.
X2 equals 1.
If you plug x2 equals 1 in, you get x1 is 2. And you get to pick that. So when you get to this point, you get to pick whatever you want for one of the variables.
Because we're going to have a constant on the... Right?
Yeah, there's always going to be a constant on this thing anyway. So one of my solutions, y1, is this vector that I found, 2, 1, times
e to the negative 3.
e to the negative 3t.
Yeah, I didn't know what that was.
C1.
I was really curious about that noise. The little cart makes a lot more sense than the other things I was thinking.
I don't know what I was thinking either.
Okay, so that's one of my solutions. To get the other one,
The same thing, but with
do the same thing with lambda's 1.
Jesus.
So in lambda's 1, you got your matrix, minus 1 on the diagonal, gives you minus 2, minus 4, minus 1, minus 2. multiplied by some other x1, x2.
So x3, x4?
Right, just, yeah, call them something different, don't confuse them with the work over there. I really like to separate those things a little bit personally. And this is supposed to be the 0 vector. And you'll notice on your second row there you get minus x3 minus 2x4 is the 0 vector, or is 0. So that would tell you x3 is 2x4. Jeff? No. What did I screw up? You can see what I screwed up?
-2 there.
Yeah, I lost a minus sign. So, minus somewhere. Doesn't matter where. Put it somewhere. Then you get to pick. So which one are you going to pick?
x4,
Pick x4 is 1. So your vector for this guy is x4 is 1, and x3 then is
-2.
-2. And so your y2 is that vector, -2, 1, multiplied by e to the t. And so your general solution is y is C1 times 2, 1 times e to the minus 3t. And this is terrible form. We're going to have a vector with a scalar multiplied by each side of it.
Yeah.
Really, probably I should rearrange this into something sensical. It doesn't actually matter which side you pick or whether you pick a side. Right? So, something like this. And then maybe on this one I'll do this one. And then this side gets the -2, 1 vector, and a constant, and a e to the t.
So this, like, maybe I should have asked this a long time ago. So on the starting out, we had, you know, the vector y prime. So if we had like the first component of that, which is like a derivative, equals -1 times something, -4 times something.
Oh, so hang on. So this thing written out would be y1 is, sorry, y1 prime
Yeah.
is very specifically -1 y1 minus 4 y2.
And so the solution to that would be C1 2 e to the minus 3t plus -2 C2. We go to the top, right?
Yeah,
Okay.
yeah. So y1 then is C1 2 C1 e to the minus 3t 2. Cool, whatever. Yeah, so the y1 is the top row, y2 is the bottom row.
I'm just confused on what's going on at the end where you're saying you're picking the values for x3 or x2 or x1 or x4 or whatever. I didn't really get that.
They
Oh,
depend
so
on each other.
this is really, there's not
Just a
just
ratio?
one vector like this, there's infinitely many.
Is it just a ratio then, pretty much?
Yeah, it's just a ratio, and I'm just picking some convenient value for that.
So you
This
can
thing's
pick-
going to get multiplied by a constant anyway. So if I hadn't done that multiplication, I would have in here x2 and 2x2.
Okay.
And then the x2 would be this c1. Right, and on the other one I'd have a x4 and a -2x4.
Okay, so it is.
So the x2 would play like c1 and the x4 would play like c2.
Mhm.
Doesn't matter. I find it easiest to just pick one. And the eigenvector is traditionally gotten by picking one. Like you just pick a value for the free variable there.
Mhm.
But certainly you could leave that arbitrary constant in there. It's just, that's not a vector, that's a whole vector space.
Oh, yeah.
Right? It's not one vector, it's like a whole,
It's like, this is
like a
our
whole
vector
line worth
line.
of vectors.
whatever x is.
Yeah.
It goes up and down.
And the negative sign doesn't matter either, you had -2 and 1, could have been 2 and -1, it would have been the same thing.
Sure, yeah, and this can be any scalar multiple of the vector minus 2, 1,
It's like
including a negative one.
like -100/50 even, it's just anything, any ratio that
Yeah.
satisfies that. Like,
Yeah, any ratio where, yeah, you could pick x4 to be negative 100 million and 36. Like, whatever, it doesn't matter at all.
I see once, that's what-
And that gets just absorbed into this arbitrary constant anyway, so who cares? Cool? Alright, I think that's what I got.